Hey everyone, welcome back to the channel. I'm thrilled you're here because today we're taking the ultimate deep dive into one of the most revolutionary models in natural language processing, BERT, and exploring its entire ecosystem of variants. We'll dissect what makes BERT special, examine every major variant in detail, understand their unique architectures, compare their performance metrics, and most importantly, help you choose the perfect BERT for your specific use case. Whether you're a researcher, developer, or just curious about AI, this comprehensive guide will give you everything you need to master the BERT universe. So grab your coffee, hit that like button, and let's dive deep into the world of BERT. BERT stands for Bidirectional Encoder Representations from Transformers. And it's not just another language model. It's a paradigm shift that changed everything we thought we knew about NLP. Let me break down what makes BERT revolutionary. Traditional language models like GPT-1 could only read text from left to right, like how we naturally read. But BERT introduced bidirectional context understanding. Imagine being able to understand a sentence by reading it forwards and backwards simultaneously. This bidirectional processing allows BERT to capture much richer contextual relationships. BERT achieves this through two ingenious pre-training tasks. First, masked language modeling, where BERT randomly masks about 15% of input tokens and learns to predict them using context from both directions. It's like playing a sophisticated fill-in-the-blanks game where the model learns deep language patterns. Second, next sentence prediction, where BERT learns whether two sentences naturally follow each other. This helps the model understand document-level coherence and relationships between sentences, crucial for tasks like question answering and text summarization. When Google released BERT in October 2018, it came in two configurations: BERT Base with 12 transformer layers, 768 hidden dimensions, 12 attention heads, and 110 million parameters. Then there's BERT Large, with 24 layers, 1,024 hidden dimensions, 16 attention heads, and a massive 340 million parameters. The impact was immediate and dramatic. BERT achieved state-of-the-art results on 11 NLP tasks, including pushing glue benchmark scores from 68.9% to 82.1%. But here's the catch. BERT is computationally expensive, memory-hungry, and sometimes overkill for specific domains. That's exactly why the research community went wild creating specialized variants. The BERT family has exploded into a vast ecosystem with dozens of variants, each resolving specific challenges. Let me organize this complexity for you. We have 5 major categories. First, the original BERT family, the foundational models that started it all, including BERT Base, BERT Large, and early improvements like RoBERTa and DeBERTa. Second, efficient BERTs, the speed demons designed for production environments. This includes compression masters like DistilBERT and TinyBERT, mobile-optimized variants like MobileBERT, and parameter-efficient models like ALBERT. Third, domain-specific BERTs, specialists trained on industry data. We're talking about BioBERT for healthcare, FinBERT for finance, LegalBERT for law, SBERT for scientific research, and many more niche variants. Fourth, multilingual BERTs, the polyglots that break language barriers. This category includes MBERT for general multilingual tasks, XLM-R for cross-lingual understanding, and language-specific variants like Camembert for French, Beto for Spanish, and IndicBERT for Indian languages. Finally, sentence-level BERTs, models that excel at understanding entire sentences rather than individual words. SBERT leads this category for semantic similarity, while LABSC handles multilingual sentence embeddings. Each variant represents years of research addressing specific limitations of the original BERT. Let's dive deep into each category. Let's start with the original BERT family, the foundation upon which everything else is built. BERT Base is your Swiss Army knife of language models. With its 12 transformer layers, it strikes the perfect balance between performance and computational efficiency. Each layer contains 768 hidden units and 12 attention heads, totaling 110 million parameters. It's trained on book corpus and English Wikipedia, about 3.3 billion words total. BERT Base consistently delivers solid performance across diverse NLP tasks without breaking your GPU budget. BERT Large is the heavyweight champion with 24 layers, 1,024 hidden units, and 16 attention heads, packing 340 million parameters. It delivers superior accuracy on complex tasks, but requires significantly more memory and compute time. Training BERT Large from scratch costs tens of thousands of dollars in cloud compute. That's why most teams use pre-trained versions. But the story doesn't end with original BERT. Roberta, developed by Facebook, showed that BERT was undertrained. By removing next sentence prediction, using larger batch sizes, training on more data for longer, and using dynamic masking, Roberta achieved better performance than BERT Large while using the same architecture. DBERT from Microsoft introduced disentangled attention, separating content and position embeddings. This architectural innovation led to even better performance, especially on tasks requiring position understanding. Electra took a completely different approach, replacing masked language modeling with a discriminative task, detecting which tokens were replaced by a generator network. This makes training 15 times more efficient while achieving comparable results. These foundational models establish the baseline performance that all other variants tried to match or exceed while solving specific challenges.
Now, let's explore the efficient BERTs, the variants that made BERT practical for real-world production systems. DistilBERT pioneered knowledge distillation for BERT. The process is fascinating. They train a smaller student network to mimic the behavior of the larger teacher BERT model. DistilBERT has only 6 layers instead of 12, reducing parameters by 40% and making it 60% faster during inference. Remarkably, it retains 97% of BERT's performance on glue tasks. The distillation process uses 3 loss functions: the original task loss, the distillation loss matching teacher predictions, and a cosine embedding loss aligning hidden states. TinyBERT pushes compression even further through a 2-stage distillation process. First, it performs general distillation during pre-training, then task-specific distillation during fine-tuning. TinyBERT achieved 7.5x parameter reduction and 9.4x speedup while maintaining over 96% performance on glue. The key innovation is distilling at multiple levels: embeddings, hidden states, attention matrices, and predictions. MobileBERT specifically targets mobile deployment with its inverted bottleneck structure, inspired by MobileNets. Instead of the standard transformer architecture, MobileBERT uses bottleneck layers that compress information through lower dimensional representations. This architecture is 4.3x smaller and 5.5x faster than BERT Base, while achieving competitive accuracy. It's optimized for ARM processors and can run efficiently on smartphones. Albert introduces 2 groundbreaking techniques: factorized embedding parameterization and cross-layer parameter sharing. Factorization separates the size of hidden layers from vocabulary embeddings, dramatically reducing parameters. Parameter sharing means all layers use the same weights, further reducing model size. An Albert XXXL model has 235 million parameters compared to BERT Large's 340 million, yet often performs better. FastBERT introduces adaptive inference, allowing early exit from the model when confidence is high. This provides dynamic computation. Simple examples exit early, while complex ones use the full model. These efficient variants prove you don't always need massive models. Smart architectural innovations can deliver comparable performance at a fraction of the computational cost. Domain-specific BERTs represent a crucial insight. Sometimes specialized knowledge trumps general intelligence. Let me walk you through the major specialists. BioBERT revolutionized biomedical NLP by continuing BERT pre-training on PubMed abstracts and PMC full-text articles, over 18 billion words of biomedical literature. This domain adaptation helps BioBERT understand complex medical terminology, drug interactions, protein names, and disease relations that confuse general models. BioBERT achieves state-of-the-art results on biomedical named entity recognition, relation extraction, and question answering tasks.
For example, on the BC5-CDR chemical disease relation task, BioBERT scores 68.2% F1 compared to BERT's 64.1%. Clinical BERT goes even deeper, training on clinical notes from intensive care units. It understands medical abbreviations, clinical workflows, and patient care terminology. This specialization proves crucial for tasks like clinical outcome prediction and medical record analysis. SBERT targets the broader scientific literature, trained on 1.14 million papers from Semantic Scholar, spanning computer science and biomedical domains. It uses a custom vocabulary built from scientific texts, helping it handle technical terminology more effectively. SBERT shows significant improvements on scientific NLP tasks like citation intent classification and scientific document summarization. FinBERT brings financial intelligence by training on financial news, SEC filings, earnings calls, and analyst reports. It understands financial jargon, market sentiment, and economic indicators. FinBERT excels at financial sentiment analysis, achieving 97% accuracy on financial news sentiment compared to 89% for vanilla BERT. It's particularly effective for algorithmic trading signals and risk assessment. Legal BERT tackles the complex world of legal language, trained on legal cases, contracts, and regulatory documents. Legal text has unique characteristics, long sentences, specialized terminology, and precise logical structures. Legal BERT significantly outperforms general models on legal tasks, like contract analysis and legal document classification. The pattern is clear. Domain-specific vocabulary and context understanding provide substantial advantages. These models prove that in specialized fields, a smaller domain expert often outperforms a larger generalist. Multilingual BERTs tackle one of AI's greatest challenges, making language understanding truly global. Let's explore how these polyglot models work. Multilingual BERT, or MBERT, was actually a happy accident. Google simply took the original BERT architecture and trained it on Wikipedia data from 104 languages simultaneously. What surprised researchers was MBERT's ability to perform cross-lingual transfer, train on one language and apply to another without explicit translation. This happens because the model learns language-agnostic representations in its deeper layers. MBERT's training data includes high-resource languages like English and German with millions of Wikipedia articles, but also low-resource languages with just thousands of articles. The model uses a shared vocabulary of 110,000 subword pieces across all languages, enabling cross-lingual understanding. XLM-R pushes multilingual understanding further by training on common crawl data from 100 languages, 2.5 terabytes of text total. Unlike MBERT, XLM-R doesn't use language embeddings or translation language modeling. Instead, it relies purely on masked language modeling across massive multilingual data. This approach yields better performance, especially for low-resource languages. The specialized multilingual variants are equally impressive. Camembert focuses exclusively on French, achieving better French NLP performance than multilingual models. It's trained on 138 gigabytes of French text from diverse sources. Similarly, Beto serves Spanish, IndicBERT covers 12 Indian languages, and AraBERT handles Arabic's unique morphological complexity. What's fascinating about multilingual models is zero-shot transfer. Perform well on languages never seen during fine-tuning. For instance, you can fine-tune MBERT on English question answering data, and it performs reasonably well on German questions without German training data. Cross-lingual alignment happens naturally through shared vocabulary and similar syntactic structures across languages. However, performance varies significantly. Closely related languages benefit more from transfer than distant language pairs.